In this lecture, we want to look at the stability of discrete control systems. We can tell the stability of a discrete control system from the positions of the poles in the z-plane. A closed-loop discrete control system is said to be asymptotically stable if and only if all the closed-loop poles lie within the unit circle. It is said to be marginally stable if there are simple real poles or simple pairs of complex poles on the unit circle, whilst all other poles are inside the unit circle. Whenever there are poles outside the unit circle or there are repeated poles on the unit circle, the system is unstable. Sampling may cause a stable continuous system to become unstable. Let's consider a system with forward TF K over S. If we close the loop, the closed loop TF becomes K over S plus K. The pole is at minus K. For the system to be stable, the pole must be in the left-hand plane. Therefore, K must be more than 0. Let's now turn the system into a discrete control system by introducing a zero-order hold DAC. The forward TF in Z domain becomes KT over Z minus 1. The closed loop TF becomes KT over Z minus 1 plus KT. The pole is at 1 minus KT. In order for the system to be stable, the pole must be inside the unit circle. Therefore, K must be more than 2 over T. We notice that in the sampled system, the range of K for stability is smaller than the range of K for stability in the continuous system. Therefore, sampling has reduced the range of K for which the system is stable. In discrete control systems, stability is tested for using the Jury's stability test. This test is performed on the closed-loop characteristic polynomial. The closed-loop characteristic polynomial is denoted as QZ. The first step in the test is to express QZ in the form shown. A0 is the coefficient for z to the power n, A1 is the coefficient for z to the power n minus 1, A2 is the coefficient for z to the power n minus 2, and so on until we get to an, which is the constant term. We must ensure that an is more than 0. The second step is to apply the necessary requirements for stability. These are: 1. The magnitude of an must be less than 1. 2. Q of 1 must be more than 0. 3. Minus 1 to the power n by q of minus 1 must be more than 0. In other words, q of minus 1 should be less than 0 if n is odd, and q of minus 1 should be more than 0 if n is even. If QZ fails any of these three requirements, the system is unstable. If QZ satisfies the three requirements, we go on to the third step, which is setting up of the Jury's table. Here is how we set up the Jury's table. The first row is made up of coefficients from the closed loop characteristic polynomial. The second row is coefficients written in a reverse order. Let's term these first two rows the A rows. After setting up the A rows, we calculate K1 defined as AN over A0. Using K1, we set up the second pair of rows that we shall term the B rows. Each element in the first B row is equal to the corresponding element in the first A row minus K1 times the corresponding element in the second A row. The second B row is equivalent to the first B row written in a reverse order. We notice that the number of elements in the rows is reduced by 1. After setting up the B rows, we calculate K2 defined as Bn-1 over B0. Using K2, we set up the third pair of rows that we shall term the C rows. Each element in the first C row is equal to the corresponding element in the first B row minus K2 times the corresponding element in the second B row. The second C row is equivalent to the first C row written in a reverse order. We also notice that the number of elements is reduced by 1. We repeat the process until we have 1 element in the rows. The system is stable if and only if the leading coefficients B0, C0, D0, etc. are all more than 0. The number of coefficients that are less than 0 is equal to the number of poles that lie outside the unit circle. Therefore, it is the number of unstable poles. A 0 coefficient indicates a pole that lies on the unit circle. Therefore, it indicates a marginally stable pole. Let's illustrate using an example. In the diagram, Gz is the TF of the process preceded by a zero-order hold DAC. Gz works out as 0.368Z plus 0.264 over Z minus 1, Z minus 0.368. The closed loop TF is Kgz over 1 plus Kgz. The closed loop characteristic equation is 1 plus Kgz equals 0. If we substitute for Gz, we obtain the equation as Z minus 1, Z minus 0.368 plus K, 0.368 plus 0.264 equals 0. Let's apply the jury's test to find the range of K for which the system is stable. From the closed loop characteristic equation, Qz equals Z squared plus open bracket 0.368K minus 1.368 close bracket Z plus 0.264K plus 0.368. Let's check the necessary conditions. The condition that the magnitude of An must be less than 1 gives the range of K as from minus 5.178 to 2.394. The condition that Q1 must be more than 0 gives the range of K as K is more than 0. Now, the system is second order, which is an even order. So we use the condition that Q minus 1 must be more than 0. If we apply this condition, we find the range of K as K must be less than 2.394. Because the system is second order, we do not need to proceed to the jury's table. The range of K that makes the system to be stable is the range of K that satisfies all the 3 conditions. This range is K is between 0 and 2.394. I recommend that you do these questions from chapter 7 before you proceed to the next lecture.